there! Welcome to the Chapter 6.8 video on analyzing graphs of polynomial functions. So what we're really going to do today is just wrap up a couple of these kind of loose ends we've been talking about. So here's just a little concept summary. So if we have a polynomial function, then the following statements are going to be equivalent. K is a zero of our function, so that's what we call it. K is a zero of our function. And if k is a 0, x minus k is a factor, right? So because if I factored it and I set my factors equal to 0, I'd get k as a 0. Then also k is a solution, because remember 0 and solution and root, they're all the same word. Okay, they mean the same thing. So k is also a solution when we set our polynomial equal to 0. And if k is a 0, then it's going to be an x-intercept. So these all mean the same thing. So if I have a solution or a root or a 0, then it's an x-intercept, and it also relates back to a factor. So we haven't graphed in a while, but if I want to graph this, if I have it factored, then I already know my zeros are my x-intercepts. So actually I need one more step here to finish factoring this. In the middle here we have a difference of squares. So this is going to, that's an equal sign. Let me try my equal sign again here. Equals -2 times x plus 3 times x minus 3 times x plus 4. So my zeros are going to be -3, +3, and -4. I'm going to zoom in here a little bit on my graph. So I'm going to have a 0 at -3, +3, and -4. And then to finish my graph, I can just make my table from there. Now going back, remembering our end behavior, this is going to be an x cubed, so odd degree, which means the ends go different ways, with a negative leading coefficient. So our ends should go up on the left and down on the right. It could be a line with a negative slope. So I'm going to make my table, and I'm going to put in a -5 and a -3.5 because I want to know what's happening between those 2 points. Maybe a 0 and a 4. I'll start there. You can plug it into this exact form where given, or if you want to, you could multiply that out and put it into a standard form. So I'm going to plug -5 into my calculator, and I get 32, which, okay, 32. Then I'm going to do -3.5. And I'm going to get -3.25. And I'll change that to a 0. And I get 72, and then to a 4, I have some large numbers here to graph. I get -112. Alright, so the idea here is, do I think this 32 is going to be the end behavior on this side? And I do. And do I think that -112 is going to be the end behavior over here? Again, I do. For the sake of getting this kind of exact, why don't we go ahead and count by tens? So we're going to make the top here be 100. So 32 would be, let me zoom in again. 32 is going to be someplace up around there. Negative 3.25 is going to be just past that. Then we're going to go up to 72, which is going to be around there. And then we're going to go down to 112, which is going to be just past it. So here we go. We're going to come down this way, turn, come up here, and go down that way. Oh, not too shabby. All right, so there is our graph. Notice on the x-axis we are counting by ones, and then on the y-axis we're counting by tens. So that last graph had two turning points, and a turning point is just, it's a local minimum or maximum, so it doesn't have to be the minimum or the maximum, just a local one. Because notice here, like this is going to go, you know, keep going down. This one over here is also going to keep going down. So I mean, they're going to become a minimum. I mean, the minimum is going to be infinity, negative infinity. So this is a local minimum. It's just a minimum in relationship to the points just right near it. And in this case also we have two local maximums. Okay. So they're turning points because you had to, you know, if you were going up, you had to turn to go back down to get that maximum point, and if you're going down, you had to turn to go back up to get that minimum point. So they are turning points. So if you have a polynomial of degree n, it's going to have at most n minus 1 turning points. So we just graphed one of degree 3 and it had 2 turning points. So at most, so it could have less than that. And if a polynomial function has n distinct real zeros, then it has to have n minus 1 turning points. So for you to have, you know, 3 real zeros, you had to turn twice. Okay, and it says distinct because we're going to get into now talking about what would be called the double root. So if that was a distinct zero, but this was a double root, then it's going to cross there, but it's not going to cross there. But you might then also ask yourself, did it still turn? Well, it has 3 zeros. Did it turn twice? So there you go. We will continue these conversations in class. Let me know if you have any questions, and have a good day.